complexity of two-party differential privacy.
So this is a joint work with Iftach and Jad Silbak and Eliad Sfadia. So let me start by defining differential privacy. So we are going to assume we have some database X that contain maybe sensitive information about the participants. And we want to publish some statistics on this database without revealing any private information on the participants. So we want to, while publishing some accurate statistic, we want to that the output of the function we published will not reveal too much information about one participant in the database. Meaning that if we imagine that one participant provides fake input to the database, the distribution of the output of the function or the mechanism we apply on the database will not change by much. It will be very close. So this is a very strong definition of privacy in the sense that even if we know the entire database but one entry, we cannot reconstruct this entry from the output of the mechanism. And to make it formal, we ask that we say that a mechanism M is epsilon delta differential private if for every two neighboring database X and X prime, neighboring it means that they are differ only in one entry. The output, the distribution of the output of M on X is epsilon delta close to the distribution of the output of M on X prime, meaning that for every distinguisher, maybe unbounded distinguisher, the probability that the distinguisher output one on the output of the mechanism on X is bounded by E to the epsilon times the probability that D output one on the output of the mechanism on X prime plus delta. And this delta is usually very small, like some negligible or 1 over large polynomial. So in this talk, we will think about this delta as 0. And epsilon is some small constant. So E to the epsilon is actually 1 plus epsilon. And this means that the probability of the distinguisher to output 1 on the output of the mechanism on X is up to 1 plus epsilon factor, the same probability as its output 1 on the output of the mechanism of X prime. And again, this is a very strong definition. Even if the distinguisher knows anything about the database except for one entry, you cannot distinguish between the real entry of the participant to the fake one. So for an example, let's assume that Tel Aviv University want to perform some survey among the students, and it want to know how many students suffers from high blood pressure. So the university collect data from the student, and now it holds a vector of length n, when n is the number of students. Each entry in the vector is equal to 1 if the student suffers from high blood pressure and 0 otherwise. And we want to publish the number of students that suffers from high blood pressure. So we want to publish the sum of the entries of the vector. And of course, if we publish this sum, then this is not a differential private mechanism, because if we know the entire vector but one entry, we can reconstruct the remaining entry by knowing the sum. So this is not differential private mechanism, but it turns out that if we add a small noise from a specific distribution called Laplace, then this mechanism is differential private. And the amount of noise we need to add is constant in the sense that it's independent from the length of the vector n. It's only dependent on epsilon. Okay, so this is a very accurate mechanism to compute the sum of a vector while preserving privacy. But this example for a differential private mechanism in the centralized model, meaning we have one party that holds the entire database, and we want to publish some function of this database. But we can imagine a situation in which we have two parties. Alice holds one database and Bob holds a second database, and they want to compute a function on the joint data. So they want to communicate in order to output some function of both x and y. This is the two-party differential privacy case, and the privacy notion we want to achieve is that the view of Alice in the protocol will preserve the privacy of the participant in the database of Bob, and the view of Bob in this protocol will preserve the privacy of the participants in the database of Alice. So we want that for every input of Alice X, and for every two neighboring databases of Bob, the view of Alice in the protocol when Alice uses X and Bob uses Y will be epsilon delta close to the view of Alice in the protocol when Alice still uses X, but Bob uses Y prime. This means that the view of Alice in the protocol preserves the privacy of the database of Bob. And the view is just the input, coins, and transcript. And we ask the same for Bob. So we want also that the view of Bob will preserve the privacy of the participants in the database of Alice. So for example, if we still, Tel Aviv University still want to do this survey of knowing how many students suffers from high blood pressure, but now each faculty want to collect the data on its own students separately. So the faculty of exact science has this vector of all the students in the exact science faculty that suffers from high blood pressures, and we have the faculty of social sciences that all a vector that for the student of the social sciences faculty. And now they want to know how many people in the entire university suffers from high blood pressure, but say that the faculty of exact science doesn't trust the faculty of social science with respect to this data. Then they want to communicate privately. And in this case, it's very simple. The faculty of exact sciences just can send a noisy estimation of the number of students in this faculty that suffers from high blood pressure. And the faculty of social sciences can do the same, and they can just add this output and compute that.
It would have same identical input lengths?
So it's just an assumption, but we don't use it in this example. So they just publish the sum of the output, and this is a very simple protocol. But this is a very simple case, and there are more complicated functions. For example, let's say that we want to measure correlation. So now Alice and Bob have two different databases on the same set of participants. Alice has a vector that says for each participant whether he smokes or not. So it's -1 if this participant smokes and 1 if it doesn't smoke. And Bob have the same for high blood pressure. And we want to compute the correlation between smoking and high blood pressure. And this is much less clear how to do. Right? But if we think about it, then the functionality we want to compute in this case is the inner product between the vector of Alice and the vector of Bob, which is exactly the correlation. So the question of this work is how complicated it is to compute the inner product between two vectors while preserving privacy. So this is the question. So what do we know? So first of all, in the centralized model, if you have one party that holds both vectors and we want just to publish the inner product, then similar to the case of the sum, we can just compute the inner product and then the Laplace noise, and we can achieve a constant error that's independent of the input. In the two-party case, so assuming that the vector of Alice and Bob chosen uniformly at random, we have a very simple protocol, just output 0. And this protocol has a noise of square root of n with very high probability. So there is a trivial protocol that achieves noise of square root of n. And unfortunately, and this can be generalized for every input distribution using the protocol called the randomized response. But unfortunately, this is the best we can do. So there is a lower bound that says that for any differential private protocol for computing the inner product, the noise must be square root of n. So we cannot do better than square root of n. But we have a centralized model mechanism that achieve constant error. And we know that using cryptography, we can simulate a trusted party that will simulate this centralized model mechanism. So using crypto, we can achieve constant error.
Crypto, can we still get this code in? I mean, not in the distributional setting, it's trivial, but when there's no distribution,
Yeah. So there is a protocol called randomized response, which achieve worst case.
Even for worst case.
So using crypto, we can achieve constant error. And this seems like contradict the lower bound, but the issue here is that the privacy only holds for computational bounded distinguishing. So in order to use this result, we need a new definition of differential privacy. And for this, we have the definition of computational differential privacy. So when we defined differential privacy, we said that this distinguishing bound should hold for every distinguisher, even unbounded bound. And in computational differential privacy, we just restrict the distinguisher to be efficient and bound.
So when you're talking about the computational protocol, are you talking about like MPC?
Yeah.
Okay.
Secure
So you
multi-
can achieve no error. You can just.
No, so if you want differential privacy,
Oh, right.
you must
You have to publish the result, right? Yeah.
Okay, so now the distinguisher is just a polytime distinguisher. And in the same way, we can define two-party computational differential private protocol, when now we require that the view of Alice in the protocol will preserve the computational differential private property with respect to the database of Bob. And the same for Bob. So now we have a definition of computational differential privacy, and now we can use a multi-party computation in order to simulate any centralized mechanism in the two-party case.
Question on in the centralized setting, what do you know about computational versus information-theoretic DP? Like, is there meaningful natural separations in the centralized setting?
So I'm not sure. I think there is with one function, but I'm not sure.
I don't know. So maybe guy. What is the difference in the centralized setting?
Yeah, there are differences. The local and the
Everybody's looking at you as we're asking you a question.
Sorry. I was distracted.
So versus information-theoretic DP in the centralized setting.
There is a work of Mark Bunn and someone will show something.
Yeah.
So now we have this secure multi-party computation, and we can take any epsilon delta centralized mechanism and convert it into a very accurate computational differential private protocol. In the case of inner product, we can take the centralized mechanism that add Laplace, which has constant error, and get a protocol that epsilon delta computational differential private protocol with a constant error. And of course, in order to use secure multi-party computation, we need to assume oblivious transfer, or OT. So we need some cryptographic assumption. And the question is, what is the complexity of two-party computational differential private? So using OT, we can get very accurate protocols, but can we do it while only assuming one-way functions? And if we cannot do it while only assuming one-way function, we will really need to assume public key cryptography, or maybe we can use more reliable assumptions. And even if we do need to use public key cryptography, do we really need to use every secure multi-party computation, or maybe we can do something more efficient? So the question in this work is, what is the complexity? Specifically, what is the complexity of inner products? So we have this complexity hierarchy when the minimal assumption for cryptography is one-way function, which is equivalent to all these nice primitives. And OT is sufficient for multi-party computation. And in the middle, we have key agreement. And we want to know where to put non-trivial distributed or two-party computational differential privacy, when non-trivial is anything that we can do in the centralized model, but any accuracy we can achieve in the centralized model or with computational differential privacy, but we cannot achieve in the two-party model with differential privacy. So we can achieve each such task using OT, and it's not hard to see that non-trivial distributed computational differential privacy imply one-way function, but we want to know where to put it between OT and one-way functions. For the special case of computing the XOR, when Alice owned 1 bit and Bob owned 1 bit, and they want to publish some estimation of the XOR, then we know that this is equivalent to OT. So for this specific task, we know that the complexity of this specific task is exactly OT. But in order to publish estimation of the XOR between Alice and Bob, the estimation need to be very noisy, because when we know the XOR and we know 1 bit, we can compute the other bit. So the accuracy of any protocol to compute XOR is very bad. So no one is going to compute XOR in a differential private way. This is not a natural task. And a more natural task is to compute the correlation or the inner product. So this is actually a more interesting question. And for this, we only know that we can use OT in order to construct it. And we knew that there is a separation from one-way function to this. So we can not use one-way function in a black box way in order to compute the inner product. But we didn't know where to put it exactly. And in our work, we showed that we can use any inner product protocol, differential private inner product protocol, in order to construct key agreement protocol. So if you want to construct such protocol, you must assume that key agreement exists.
And what is special about inner product in your result? Like what property does it generalize to other?
No, so the construction of the protocol that we will see is use some properties of the inner product, and we cannot generalize it for other properties. It does that, for example, for the Hamming distance, because there is a simple reduction between Hamming distance to inner product. So any functionality that you can prove a reduction from it to inner product.
So you don't have like a clear way to specify the properties in some.
So we will see. It should be. It's not very clear. It's like exactly inner product.
This is inner product over the integers. If you do it mod 2, then it reduces to x.
Yeah, if you do it mod 2.
What do you have any restrictions on the round complexity, or?
No, so we actually take inner product protocol with any number of rounds, and we can create a key agreement with, I guess, 1 or 2 more rounds.
Again, what is your definition of non-trivial?
Non-trivial is anything you can do in the with computational differential privacy, but you cannot do differential.
So how many rounds is your final protocol? Sorry.
So it depends on the number of rounds of the inner product protocol. But I think we have something like 5 rounds.
Okay.
So now the other way we don't know, right? We don't know if you need key agreement or OT.
Right, but there is a very recent result that showed that key agreement is not enough.
The black box.
In a block box. And we will use some more relaxed definition of differential privacy. We only need the protocol to be differential private with respect to outside distinguisher. So we only want the transcript to respect the differential private of both Alice and Bob, and then it's equivalent to key agreement. So we don't know how to use the fact that the differential privacy property should hold with respect to Alice and Bob in order to get OT, but we believe that the right answer is it.
No, sorry, why you answered this just now, but I don't understand. Why do you need the word non-trivial in that green box? What if you just wrote CDP IP?
So we will see the exact result.
But then you don't need crypto. I mean, if it's
If it's almost output 0. differently.
Yeah, like there is the protocol, the simple protocol that just starts with 0.
Better than randomized response.
Yeah, exactly.
Anything
I
better
see
than
it.
We will see the exact. So here is the exact claim. So let's assume that pi is a protocol which is epsilon delta computational differential private for small enough delta, that for some number L satisfies that if we choose the input at random and compute the output of the protocol, the distance between the output of the protocol to the real inner product is smaller than L with probability larger than L over square root of L. If we have such guarantee, we can use the protocol pi in order to construct K-element protocol.
Yeah, in a product that should compute over the integers.
Yeah. So if we take epsilon to be constant and L to be square root of n over c, then we get that any protocol with accuracy with constant probability less than square root of n implies K-element. Right? So this reproves the information-theoretic result. We cannot have real differential private protocol that has accuracy less than square root of n with high probability because we can use such protocol to construct K-element. And more generally, so I said that this is true for any L. We actually need this L to be larger than log L. But other than this, this is tight up to a constant in the sense that the protocol that just output 0 has error at most L with probability L over square root of L. So if we get something which is a little better than the trivial protocol, we can use it in order to construct K-element. Okay, so let's see the information-theoretic proof.
One slide back. Where is the delta exactly? Like it says delta above the right.
Yeah.
Where do you use delta exactly?
So we just need delta to be small enough.
Just in mind, what does the delta represent?
So in the definition of differential privacy, we will. But we can think about this delta. So let's see the information-theoretic, the idea behind the information-theoretic law about. So assume we have a protocol pi, which is epsilon differential private, and we choose the inputs x and y uniformly at random, and then we run the protocol and get a transcript T. And if this protocol pi is accurate protocol for the inner product, then this transcript T contains estimation to the inner product, accurate estimation to the inner product. Then so if you have such pi, then it's for any protocol, it holds that the input of Alice given the transcript is independent from the input of Bob given the transcript. So X given T and Y given T are independent random variables. This is true for every two-party protocol. And a second property we have from the epsilon differential privacy is that if we know all the transcript and the entire vector X, but one entry, we cannot reconstruct the last entry. So the Xi is unpredictable given the transcript and X minus I for every coordinate I. And such sources that has this property called strong Santa-Vazirani source. So X given T is a strong Santa-Vazirani source, and Y given T is a strong Santa-Vazirani source, and they are both independent strong Santa-Vazirani sources. And it turns out that the inner product is a good extractor for such sources. So if we take two strong Santa-Vazirani sources, which is independent, we get and take the value of the inner product modulus square root of n, we get a uniform output. But if the transcript contains accurate estimation to the inner product, then the inner product of X and Y given T should be not random. It should be around the estimation. So this means that any epsilon differential privacy protocol for the inner product has noise at least square root of n.
Number one is just the fact.
Yeah, number one is true for every two particles.
Yeah.
Okay, so this is the information theoretic case, and now we want to use it in order to prove the computational case. So in the computational case, now pi is a computational differential private protocol. And it's still true that X and Y are independent given the concept. This is still true. But now X and Y are only computationally strong Santa-Vazirani sources, in the sense that any computational bounded adversary cannot reconstruct any entry of X given the X minus I, but information theoretically, it may be possible to do so. And for such sources, inner product is not a good extractor. For independent computational strong Santa-Vazirani sources, inner product is not a good extractor. And this also because if we assume that OT exists, then we have a very accurate protocol for the inner product. And then the inner product given the transcript of this protocol is fixed or is close to the estimation of the output of the protocol. So this proves that assuming that OT exists, the inner product is not a good extractor. So what happened here? We have two sources which are independent and no computational bounded algorithm can reconstruct a bit from it given the other bit. So it's computationally strong Santa-Vazirani sources. So in the eyes of computational bounded algorithm, these sources are Santa-Vazirani and they should be independent. So the inner product should have noise. It should be extractor, but it isn't. So this implies that in the eyes of computational bounded adversaries, there is a correlation between X and Y. So in the eyes of computational bounded adversaries, X and I and Y are not independent. There is a dependency between them. And our goal in the in order to use such a protocol, in order to construct key agreement protocol, is to extract this correlation. We want to extract this dependency to get a key agreement protocol. Okay, so let's see
the correlation is in the eye of the adversary, eye of the party.
Right, but we only need to get this correlation against Eve. So we only need to simulate this against Basari. So this is just an intuition. We will see that.
You don't want to get the correlation against Eve. You want Eve to know nothing about the key and to have a correlation between Alice and Bob. So
right, we will. Right. So
it's actually Eve knows that in the eyes of Eve are very correlated because the inner product appears in transcript.
So think about.
I'm talking in the key agreement. So you're saying in the key agreement, it's not just in the eye of Eve. The two parties have a correlated key. It's like
correlated. Key agreement exactly.
Yeah.
An example with a very
it's not like computationally correlated. It's really correlated.
So think about one bit key agreement, right? So in the eyes of given the transcript, the output of Alice and Bob are independent. So there is no correlation given the transcript between Alice and Bob. But in the eyes of Eve, the output of Alice is with probability α0 and with probability α1, and the output of Bob is also, but there are correlation. There is a dependency between them. So this is a computational correlation. In the reality, there is no correlation between the output of Alice and the output of
Because they're fixed.
or maybe fixed. So yeah. So in this sense, there is a computational correlation. Okay, so if I lost you so far, this is a great point to come back. We are going to see how to take inner product protocol and to convert it into a key agreement protocol. So we are taking an inner product protocol and construct a key agreement protocol. This protocol it's not going to be a really key agreement protocol. It's only will have some weak notion of agreement and security, but I will explain what we get after we will see the protocol. So in the first step of the protocol, Alice is just going to choose a random input, and Bob is also going to choose a random vector of length m, and they are going to run the inner product protocol in order to get an estimation for the inner product between the vectors. This is the first step. And now Alice is going to choose a random vector in 0, 1 to the n. So we are going to think about this vector as a set. And she's going to send the R vector x restricted on the set R. So she is going to send xr, which is xi for each entry I for which ri is equal to 1. So So up to an ordering of the entries in the set, she's going to send one alpha array.
Possible that she sends nothing if all zeros.
Yes, it's possible that she says. And Bob is going to send the complementary set. So he's going to send y minus r, which is yi for every entry for which ri is equal to 0. So Bob sends the complementary set. And now both of them can compute the inner product on the vectors they have. So Bob can compute the inner product between xr and yr, and Alice can compute the inner product between x minus r and y minus r.
So he also sends out, oh yeah, okay.
Yeah.
That's not private, right?
This not.
Why
So-
do you say? Because this probably have you get x.
You don't need it to be private.
So the point is that Eve doesn't know yr, so she cannot compute the inner product between xr and y.
Yeah, but sorry, when you say differential private, don't you want to say that?
The inner product protocol is differential private, but this protocol is just a key agreement protocol, so it shouldn't be.
Oh, okay.
So now just notice that if so the output of Bob is going to be xr, the inner product between xr and yr, and the output of Alice is going to be the output of the inner product protocol minus x minus r and y. And just notice that if the output of the inner product protocol is equal to the inner product between x and y, then Alice and Bob agree. Because the sum of the inner product between xr and yr plus x minus r and y minus r is exactly the inner product between x. And more generally, the agreement of this protocol says that the distance between the output of Alice to the output of Bob is exactly the noise of the protocol. So if the inner product protocol is accurate, then the output of Alice and output of Bob are close to each other. And what we need to achieve for secrecy is that no algorithm if that get the transcript of the inner product protocol, the set R, X, R, and Y minus R, all the transcript of the key agreement protocol. For each polynomial time adversary if, we want that the output of this algorithm will be far from the output of Bob. And in order to amplify this protocol into key agreement, we need that with some probability, the output of Eve will be more far from the output of Bob than the output of Alice. So Alice has some advantage over Eve in guessing the output of Bob. And this will be enough. And the intuition is that since Eve doesn't know YR, and YR is very unpredictable given the old transcript of this protocol, the inner product of XR and YR should be random or closed or with high entropy. But the proof is not trivial, and it uses a new theorem about strong Santander sources. But in a special case in which the error of the inner product protocol is small, then when the expected error of this protocol is smaller than square root of n over some polylog, then the proof is relatively simple. I don't think I have time to show you it, but the proof is not very complicated.
So I think about it that the output that the adversary sees from this protocol is like the inner product of x and y plus some of loss noise. So magnitude 1 over epsilon.
Yeah.
Could be the case.
Yeah.
So now again, so Alice and Bob are kind of like within 1 over epsilon of each other. Or Alice can guess Bob up to this 1 over epsilon error. And for Eve, you have information about what the what the error should be.
So it should be around square root of n, because if you take two independent Santander sources and multiply them, you get a noise of square root of n. So this is what we expect to see. So maybe we will see a simple example. to prove this lower bound, we get a new theorem about strong Santer-Vazirani sources, and the theorem is a C-dependent condenser for strong Santer-Vazirani sources. So we actually proved that if X and Y are strong Santer-Vazirani sources, and we choose a seed R uniformly at random, and then we look on the inner product between XR and YR, then this inner product has I mean entropy larger than square root of n over log n, even if we see the seed R and some leakage dependent about X and Y. So we get also XR and Y minus R. This still has I mean entropy. So this is C-dependent leakage, and still we can get some mean entropy. And the proof is by constructive proof. So we have an efficient algorithm, reconstruction algorithm rec, that given an index I and this leakage can reconstruct a bit of X and Y too well. And then this also holds from computationally strong Santer-Vazirani sources. So this is a second theorem we have.
What quick question? If you remove the computational part, then is it trivial?
No, so it's not trivial when you have a leakage, C-dependent leakage. But if you don't have this leakage, then this just follows from the fact that two strong Santer-Vazirani sources, the inner product of strong Santer-Vazirani sources is a good extract.
If you take the information-theoretic proof, is it enough to observe that this proof is constructive? Or
No, the information-theoretic proof is not constructive.
It's not constructive. So you get a different information-theoretic proof.
Yeah. Okay, so I think I don't have time to show you the ideas from the proof, but again, in the simple case, the proof is very simple. It's what
Simple case where they're close.
when the noise is bounded on expectation. The noise can be large, it can be square root of n, but the expected noise is not square root of n over log. Yeah, so in the general case, the noise should be smaller than L with a small probability. So the probability that the error is small can be very, very small. In the simple case, we assume that the noise can be large, but it holds for like with very high probability. So this is why the proof is simple. So to conclude, we showed that non-trivial computational differential private protocol for the inner product imply key agreement. And open question is finding a more general characterization that capture more functionalities, more than the inner product, and determine whether we need OT or we can use only key agreement protocol. And as I said, our result is tied for differential privacy against external observers. So in this case, key agreement is enough.
Question: what do you mean by DP against external observer?
So we only want that someone that sees the transcript will not get any information about the index.
Oh, so you don't mean Alice and Bob?
Yeah.
Oh, I see.
So what do you mean required for like CP IP? Like, because we showed
So we showed this.
just to do like an accurate one, or we showed that we could do an inaccurate one.
We showed that we must use key agreement in order to get accurate inner product. And the question is if key agreement is enough, or maybe we need to use
I see. I see. Because we showed that even if you have key agreement, then your protocol is not that good. It doesn't produce very good.
So we only know how to construct such protocol from OT. We don't know how to do it from PLN.
Okay, I see.
The question is if this OT is necessary. So it's like
Number one.